When a charge moves in a magnetic field, it will be exerted on by a magnetic force, but there is no force. No, the magnetic force is zero. When there are two cases. Okay, the charge is stationary, doesn't move. Okay, does not move in the field. That is one case. Okay, and the second case is that the charge move parallel to the field lines. Velocity of the charge is parallel to the field lines. Okay, yeah. It's two cases where the magnetic force is zero. The most important thing of the the magnetic force is that the magnetic force is always perpendicular to both velocity and magnetic field, determined by left-hand rule. It's always perpendicular to both magnetic field and velocity. Okay, I'm looking for a picture of the three things here, determined by left-hand rule. Yeah. And the equation for magnetic force is F equal QVB, and sine the angle theta. Okay, the angle between the field and let me write the letter theta. QVB times sine theta. Okay, and that theta is the angle between the velocity and the field, and it's usually 90 degrees. Okay, when that angle is 90 degrees, the charge will move circularly in a circle in the field. Okay, and that force is centrifugal force. So that is usually centrifugal force. And therefore, a charged particle that move perpendicular to the field will follow a circular path. Okay.
Yep.
Moving perpendicular to the field will follow a circular path. That is the most of the case, 90%. But sometimes there's another case which is much more complicated and rarely seen in the exam questions. That is the case when the charge move a helical path in the field, not circularly, okay, but helically. That is when the velocity of the charge is not perpendicular to the field. When the velocity of the charge is not at right angle or perpendicular to the field, but making an angle less than 90 degrees. Okay, it follow a helical path, because it is very rarely seen. So I just mentioned it as an introduction, not deep into the explanation and example of it. Okay.
Okay.
Like only seen once in 20 years. Okay, so this is a demonstration of the effect of magnetic force. We can see in experiment magnetic force on charge or circular motion. Here. With a device called Helmholtz coil, that it can produce a magnetic field that is uniform, parallel, okay, in the direction out of the screen we're seeing. And the field can be very strong and can be verified and can be changed its magnitude. Okay.
Yep.
And inside, this is a device with a filament that we can use an electric current to release the electrons, hitting the filament up, releasing the electrons, and the electron move in this vacuum tube containing little noble gas, not perfectly vacuum, but there's some noble gas inside with spherical chamber. Okay, so that when the electron move in it, those electrons will collide with the noble gas. For example, noble gas. Looking for the name, a specific name of those gas, probably helium, okay, or argon, okay. And according to this video, we see the color very like violet, huh? So that normal gas could be argon, okay. The electrons collide with the argon's molecule and will emit the light, so that we see this is the path of electron before turning on the magnetic field. Okay.
Yep.
When we turn, okay, he's using a magnet, and we can see that magnet can affect, can cause the force on those electrons and bend those electron path. Okay. That magnet, okay, they can push the electron. Okay.
Yep.
Now he will turn on the magnetic field generator. And that uniform magnetic field will bend the path of the electron and increasing the strength of the magnetic field until it is great enough to be a centrifugal force, making electron follow a circular path. Okay, like this.
Yep.
So that is the demonstration of we actually can see the effect of magnetic field on charged particle, like in this case. Return to the question here. Charged particle move in circular radius in a uniform magnetic field. The field at right angle, meaning it will follow a circular path to the velocity of the particle. After half revolution, the change of the particle kinetic energy is zero, because the magnetic force is always perpendicular to the velocity. Therefore, it will not change the speed. It only changes the direction of the velocity. It is centrifugal force, okay? Yeah. And therefore, velocity does speed does not change, only change direction, and therefore the kinetic energy does not change. The magnetic force is always perpendicular to the displacement and the velocity. It only changes the direction, not the speed. Hence, the kinetic energy does not change. Okay, which means the change is zero. Answer A. We have studied the topic 6, circular motion, right? Yeah. About centrifugal force. 1/2. No, not 1/2. Centrifugal force is mv squared over r. Yeah. So we probably wouldn't review that topic next time because it closely relates a lot to this topic about magnetic force.
Okay.
Yeah. And there's another kind of magnetic force that acts on a current, meaning the flow of the charge in a conductor. Okay, because the current is basically the flow of charge. The magnetic force acts on moving charge, therefore it will act on this conductor, this Y. Okay, and therefore we still use the same thing, the same rule, left-hand rule, to determine the direction of the magnetic force on this current. Okay.
Yep.
That's too small. the equation for magnetic force on that current is also given in the booklet, which is IBL. Okay, I the current, B the field, L the length of the conductor in the field, and also sine of the angle theta, where that angle is the angle between the current and the field. Okay, given the booklet. I is the current, B is the field intensity measured in Tesla. Okay, current is measured in ampere, and L is the length of the Y in the field measured in meter. Okay.
Yep.
The next question below here. About the force on charged particles. Negatively charged particle at rest in a magnetic field, the force on it is
A.
No, it is here. This is a theory that I have just mentioned. When the charge does not move in the field, there's no magnetic force. And you can also use the equation F equal QVB. Velocity V is 0, stationary, and therefore the force will be 0.
Oh, okay.
Question 7. Electron enters the region magnetic field. Use the left-hand rule to determine the direction of the force on it, on the electron. In which case, the force is toward the bottom, meaning downward. In the FBI rule, FBI left-hand rule, the middle fingers is the direction of the current, okay?
Yeah.
And current is the direction of the positive charged particles. Therefore, for negative particle, electron in this case, the direction of the current I is opposite to the direction of electrons, okay? So using FBI rule, the force is downward like this. B the field, the force is this thumb, and we want it to be downward, okay? This is the direction of the current, which is opposite to the velocity of electrons. So that is to the left, okay? So the field is this first finger, okay?
Yeah.
First finger. So the field is out of the plane, and out the page is this case, okay? You got it? Can you check that left-hand rule? Remember the middle finger here indicates direction of the current, which is opposite to the velocity of electron, to the left.
I thought it was into the...
Into, yes. The field is into the page, which is the case C.
Oh, okay. Yeah, I got it.
So I will put a note here. The direction of the current, which is the middle finger, is opposite to the velocity of the negative charge. Okay, that is the key of this kind of questions.